Hello, I'm Eamon Barrett, and I'm presenting our paper on a compliant mechanism with progressive stiffness for robotic actuation by myself, Jörn Malzahn, and Nikos Tsagarakis from the Humanoids and Human-Centered Mechatronics group of the Italian Institute of Technology. I will begin this presentation with a quick motivation for this work on robotic actuation, series elasticity, and progressive stiffness, and I will then present our mechanism's working principle and some important design parameters, as well as the design of two prototypes as distinct implementations of the mechanism. Then I will present the experimental setup and results before coming to the conclusions. And I'm starting with some basic background on robotic actuation and a brief introduction of the most common schemes. The traditional scheme for position-controlled industrial robots is to make the actuators and links as stiff as possible to prevent oscillations. In order to allow physical interactions with general environments, torque sensors have to be added so that you can get active force control or impedance control. The advantage is that with these high stiffnesses, you can get very high control bandwidths, but you cannot absorb unplanned collisions and impacts which can break the gearbox. In the next scheme, series elastic actuation, this problem is solved by adding a spring between the load and the gearbox. This way you decouple the inertias for more robustness, and you also allow energy storage in the spring. And the spring can now also be used as a torque sensor, for instance by measuring the spring deflection. A drawback, however, is that the compliance of the spring now limits the control bandwidth of the actuator. The newest scheme for highly dynamic actuation are direct drive or quasi-direct drive actuators, with no or only a small transmission between the motor and the load. Because there's no high transmission ratio, you get very high bandwidth, transparency, and robustness, but at a cost of lower output torque capacity and much lower energy efficiency of the actuators. All of these schemes have advantages and disadvantages, and our group has focused on the development of series elastic actuators. But there are of course some things you need to consider when adding compliance to the drivetrain, namely what effect different stiffnesses have on the performance and which are the trade-offs you must make. Softer series elastic actuators display higher torque resolution and better torque transparency, which is good for soft physical interactions of robots with their environment. Stiffer series elastic actuators, on the other hand, favor fast, strong, and powerful physical interaction between the robot and the environment. And the idea behind this work is now that with a progressive spring characteristic, we can have the best of both worlds. We can have high sensitivity and transparency at low loads, and at higher torques, we can still deliver high power, high bandwidth performance. And there's a couple of ways how progressive springs can be realized. Firstly, by choosing nonlinear spring materials like rubber, and that could be, for instance, bungee cords or pneumatic muscles, but this generally also adds hysteresis. You can use linear materials, but with a nonlinear geometry, for instance, coil springs with a variable pitch or radius. Or you can use linear springs, but with some mechanism that generates a nonlinear transmission, for instance with cams or tendon systems. These are also found a lot in variable stiffness actuators, especially in antagonistic VSAs, but they usually lead to bulky springs or additional complex and bulky mechanisms or transmissions. And this is our proposed mechanism, which consists of radially oriented linear extension springs that connect an inner and outer ring, without any additional components or transmissions. And as the mechanism is rotated, there are actually two effects that create nonlinearity and make the torque deflection characteristic progressive. Firstly, we have the nonlinear stretching of the spring, and you can see it when we zoom into one of the springs here. Now, the distal end of the spring follows the outer ring when it's deflected, while the proximal end is attached to the inner ring. So if the spring wouldn't be stretched, then the distal end would have to follow the smaller circle. But of course, it's being extended to follow the outer ring. And you can see that this stretching is nonlinear and progressive. For small angles, there's barely any stretching, and for larger angles, we get these finite elongations, delta L. So the nonlinear stretching generates a nonlinear spring force. The second effect we have is that also the alignment of the internal forces changes as the mechanism is deflected. We can see here that the spring force always points in the same direction as the spring. So in the initial configuration, it is orthogonal to the output deflection and doesn't generate a torque. But as the output is deflected, the spring force starts to align more with the applied deflection, and the tangential component of the spring force becomes larger. We see the mechanism here and some of the variables that determine its behavior, and it's important to understand the influence of the design parameters on the performance. In the paper, we look at everything in more detail, but here I'm just giving a global overview. So we get all the angles and lengths with some trigonometry, and then we get this expression for the output torque as a function of the deflection. And in here we of course have the spring stiffness K and the outer radius R, but also these design parameters. And we define lambda as the ratio of inner and outer radii, and zeta as the degree of pretension of the springs. And without too much math, we can already think about the effects of these parameters. We've seen before that the nonlinear tensioning of the spring is an important mechanism to achieve the progressive stiffness. But if we pretension the spring, we reduce this effect because it gets dominated by the pretension, and we can see that in the expression of the torque here. The other important parameter we have is lambda, and that determines how an output deflection affects the springs. We can look at the limit cases, and if we, for instance, make lambda 0, that would mean the proximal end of the spring is attached in the center, which means it wouldn't be stretched at all when the mechanism is deflected, and we get no output torque. If we make lambda 1, on the other hand, the mechanism looks more like this. This is compact, a linear SEA, and also in this case, the springs are already aligned to act tangentially with the output, so we would lose the nonlinearity. So here we get a trade-off between how progressive the mechanism is and its output torque capacity. Here we have a first prototype design, which is based on coil extension springs with an inner and outer ring connected through radial springs. And in this case, the inner ring is the input and the outer ring is the output, and the springs are just hooked behind pins. And this simple design already works well to show that the theory works. We can even adjust the pretension by taking different diameter pins that pre-stretch the springs more or less. This is a pretty direct realization of the design, and with the coil springs we get a medium stiffness and a pretty large passive deflection range. Now we also have another realization of the design, and this one is a bit more abstract. Instead of the coil springs, we can use radial flexure beams as our tension springs. This is maybe a bit unusual because normally you only consider bending in flexures, but of course they also have a tensional stiffness along the axis. Like before, we have the beams arranged like spokes on a wheel, but this time the springs have to be bent as well as stretched. We still need relatively large, non-infinitesimal deflections for the principle to work, so we need quite slender beams that offer relatively little resistance to bending. We can then calculate the output torque as a superposition of the contributions from bending and the contribution of the stretching of the radial tension springs, which is the same as before. The flexure beam design does have a higher stiffness and also a smaller deflection range, just because we are limited by how far we can bend the beams. But that means we can use a small angle approximation to express the torque. And if we take the Taylor expansion and assume there's no pretension in the beams, then we get this polynomial torque. And the linear and cubic term makes this a Duffing spring, which is quite helpful for describing the dynamics of the system. For the second prototype design, we keep things simple again and just use the 3D printer to make our demonstrator. We have an inner and outer ring, and they're connected through the radial flexure beams. We prepared two different beam widths, 0.7 and 1.4 millimeters, and you can see in the FEM results of the thicker beam here that we have pretty large bending stresses, but also that there are these normal stresses from the stretching throughout the beam. And as material, we just use ABS from the printer, and we didn't optimize the beam shape either. Again, just to keep things simple and have a little demonstrator for now. Now we come to the setup used to characterize the springs. And we just mount the prototypes on one of the Robotics actuators from our lab. Add a torque sensor and lock the output. And with the locked output, the spring deflection is equal to the actuator position that we measure with an integrated encoder. The actuator also already has a torque sensor, but with the external one, we just get a nicer resolution. And then we let the actuator track a sinusoidal position reference and get the torque deflection curves. And this is what it looks like in action, where you can see the outer ring and the torque sensor locked, and the inner ring connected to the actuator output moving back and forth. we can see the large deflection range of the coil spring design, which leads to large energy storage. And for the flexure beam design, we can see the more moderate deflection range, which is limited by how far we can bend the flexure beams. And here are the torque deflection plots for the coil spring prototypes on the left and the flexure beam prototypes on the right. You can see the progressive characteristic in both designs, as well as a pretty good match between theory and experiments, which is even a bit nicer on the more basic coil spring design. For the coil springs, we can see 3 different curves for different levels of spring pretension. And as predicted, the initial stiffness is higher for higher pretension, but the progressive nonlinearity is much more pronounced for low pretension. For the flexure beams on the right, you can see that the thicker beam has the higher initial stiffness, but that the thinner beam is much more progressive. You can also see that both prototype designs show very little hysteresis, even in the simple implementation, which is crucial for precise measurement and control. So we've seen that progressive SEAs have the potential to remedy a number of drawbacks and trade-offs for this class of actuators, which make them a compelling solution for robotic actuation. Our design presents a novel and simple mechanism that can achieve this goal without adding complex and bulky transmissions or special springs. We present 2 distinct implementations, one based on coil springs and one on flexure beams, which complement each other and can be each suitable for different applications. Our prototype demonstrators show the mechanism performance and validate the analytic and numeric solutions, and are ready to be properly integrated into high-performance actuators. Thank you very much.